on the classical dyadic interval from 2 to the j to 2 to the j plus 1. So on such a interval, my liquid gamma is going to be linear, so it's going to have the form mj plus b. So mj is the slope, and you have some y-intercept. Okay. So all I have to tell you, I'm going to consider two examples here. Okay, the first example, let me just remind myself. So the first example, so I just have to tell you really what gamma does on the point 2 to the j. That'll pin down the curve. So it's just j times 2 to the j. Okay, so you can make the computation very easy. The slope of this plate takes m sub j. If you do it, as I did it earlier, you get j plus 2. Okay. Okay, so this is actually a set of lines now, and it's built for arithmetic. So this is very significant k set for the set of directions. But nevertheless, it turns out that the corresponding maximal function is bounded on L2. Okay, so we'll come back to that. It's like why, right? But also, it turns out you have unbounded results. Okay, now my general construction is not going to give you any assumption for LP, but you can take a different lattice that's more adapted to the geometry of this particular example, and you can place your small characteristic small balls, and in fact, Mike did this. He showed us that in fact, for this example, you're not going to get any LP boundedness in a range, and the range you got is over 4/3. Okay, so you can actually tweak Mike's argument a little bit and improve this slightly, and you can get unbounded in the range plus 2 or 3 halves. So this is an observation of Andreas Singer, Langer, and this is an interesting question. Yet another question is between 3 halves and 2, we don't know. Okay, but that's the first example. Look at the second example. Okay, and when you say gamma of 2 to the j, to be 2 to the 2j. This is taking a classical parabola t squared and just polygonalize it at the point t equals 2 to the j. Okay, you make a computation, you see that the slope in this case 3 times 2 to the j, so these are geometric. Okay, and you can't apply necessarily the theorem of Pagel-Langer to this because they're not center line, but you can modify their argument, and you can show that the corresponding maximal function is bounded on all LP. Okay, so this is actually a result that's contained in the famous paper of 8. Okay, so usually people refer to this as CCC, a little bit of, the freezer pre-authors that they get their name given. Let's see, it's a little important. So let me try to remember, I know that I'm pretty sure one of these things, I think word about Carlson, and then Karina Ratia, Langer, and even one. Airport, I think it's from like it goes to Congress, and check with collaborations and the parts of the business. No, I've heard of many because I have co-author of a paper by Gary Levine, and number of co-authors. He said, well, anyway, okay. So we have this other result now. You can have the like results. So this is what you can ask, what does Mike's argument give you? And so if you look at Mike's argument, you get unboundedness on a scale of ordinate basis, and if you do the computation, you get some L log for some or L. Sometimes you can get one for anything with log L. So I have no idea whether L squared for log L is appropriate for this algorithm, just for log L is based on algorithm. It doesn't appear quite often. You have any point space or classical or any point space for real life. You get boundedness on the space that is no better. Okay, so these are lots of questions here. Now what I want to do is I want to so now I'm going to have to do the part that okay, this is the important part. Let's see, I know that Herbert gave me a tutorial on this. Let's see, what should good question. Okay, anyway. Use this, right? Cross down. Shift now. It takes back functions along curves. assumption, then I'm going to assume also that this is convex. Okay, I'm going to tell you why I'm going to make this assumption. Even with this assumption, there are lots of examples of convex curves, either smooth ones, or the LP boundedness of these operators are unbounded on all LP. But we've already seen examples, like velocity c squared, we've already seen examples where this is bounded on all LP. Okay, now why do I make this complexity assumption? It actually, there's a good reason for this. It's just simplified it out in the following way. If I go back, now I'm thinking about a general curve, I can think about which is averaging along the curve, and again I can go back and the average on dyadic pieces, they rotate to h. Okay, so let's say this is just averaging. It rotates to h, and I can just restrict myself to h dyadic if I like. And now one of the key things when you look at these singular maximal operators, how you get your hands on it, using the technique is using the analytic technique square function. And so there's a way that you can test if you underline averages dividing the maximal and test the smoothing. Let's get from those spaces or LP spaces. If there's some smoothing, then you can prove positive results. Yes, this goes back to the work of Eli and all his collaborators. So let's look. One way to test smoothing of a particular measure is to understand the decay of the Fourier transform. So let's use the Fourier transform. This is a measure on the plane. So I'm going to assume it's an interval that rotates to h from e to the other ct, but e to gamma t. Okay, and I want to understand how the angle is theta. So you have to understand where this phase becomes stationary. Okay, and now notice that the critical, so in other words, the critical points of this stage are very simple. Okay, there's at most one critical point. So that's if it's strictly convex, but if it's but in general, if it's just a single interval of critical points, we'll just say it gamma is convex. Okay, so the convexity assumption tells you that the geometry of the critical points is the same. Very, very simple. That's a single point or an interval. Okay, so that's what. So I'm going to make this underlying assumption, and here the goal I'm going to propose. I don't know how feasible this is, but it is to try to find a nice necessary and sufficient condition on the curve gamma, so there's a just a curve which is convex, that guarantees that the corresponding maximal function is bounded on L2. Okay, so I don't know how feasible this is. Certainly Steve Wanger would like to, he would love to see this goal realized some way. You might add YL2, doesn't necessarily mean that the natural space necessarily with maximal functions. Of course, the technique, the analytic technique with square functions is natural from that point of view, but we've already seen an obstruction on L2, certain methods to work. You could also think about Mike's counterexamples, and I don't, they tend not to work beyond L2. I don't think that there's been an example. I don't know, for instance, of a nice convex curve in the plane where you get unboundedness for a range of t bigger than 2, and then it becomes bounded. I don't know an example, for instance. Okay? So that might have some possible obstruction, but anyway. So I'm going to write this as a goal. It is true. Let me just pause for a second. Okay? And can I pause? Am I on time already? Where do we start? Now we're doing? Oh, okay. Geez, sorry. I'm getting later. Okay. Okay. I should have drank that coffee. There are other situations. Here's a situation that's somewhat related to these type of maximal functions. Instead of averaging, look at maximal functions where you average along gamma, I'm going to average over gamma. Suppose I take a convex curve, a compact convex curve in the plane, so the origin is somewhere in the middle, and I'm now going to look at an average over it, say with respect to arc length measure, d sigma, which I'll assume can be normalized at mass 1. So I'm going to look at convolution over this, so this averaging operator, and then I'm going to consider dilates of this, but I'm only going to consider lacunary dilates, and take the supremum over all lacunary radii, and that gives me a maximal function. I'll call that n sub gamma. So it's a lacunary maximal function. So for instance, if you consider all radii, and you just have a circle that's the same as circular maximal function. But in this case, when you take lacunary dilate, it's well known, quite easy to prove that if this curve is finite type, that is, there's no point on the curve that the curve dimension is in order, so you get LP boundedness for all t bigger than 1. Such a thing. And it's a big unsolved problem. Even for the circle, whether this lacunary maximal function is B type 1, we don't know. So that's another interesting problem. Now, what I'm going to look at is a condition on this curve. I'm going to now be allowing the curvature to vanish in order, but I'm only going to try to characterize the L2 bound. So here's a condition which says that. So what I'm going to do is I take a point on the curve, I'm going to now define a little cap around it. I'm going to take the tangent line here, go in a normal direction, find out delta, look at the parallel line, and then cut off the cap. So what if I'm thinking it's huge? That's the flight technology here. So there's the cap, I'll call that C. So then a T radius delta. So if I take the arc length measure of this guy here, and I look at this, the condition is asking it to be square summable with respect to these various measures, d delta over delta. I integrate the full delta say, and take the supremum over all the points in the curve, and I'm going to ask when it's finite. So I'll call this condition C. Okay, so that you can check. I have to do some more. So you can check that there are certain that allows for flat examples, but not all flat examples. Okay. Let me try this out. Sorry. But there's another question that we don't know how to do. Now let me go back to these curves, this maximum function along convex curves, okay, and tell you a little bit of a difference between, we introduced them by these polygonal line configurations and compared them with what happens when everything is centered. So the difference with the centered line configuration that we have for these operators, here's the difference, is that there is a natural singular interval operator associated to this curve called the Hilbert transform along the curve. So we're just convolving along the curve, but we're putting a classical Hilbert transform singularity dt over t. You have to find the principal value sense. Okay, so this actually, these singular add-on transforms actually arose from a different problem. It was trying to generalize Polar Sigmund theory, the method of rotations to other dilation groups. So here, I have to tell you, because so the maximum function is only defined for t positive, I have to tell you what's going on for t negative. So I have this nice convex curve here, and so how I define it is going to tell me what the cancellation is. And it's important how I do it, and I'm only going to do it not just one way, in an odd way, I'll call it odd, or in an even way, I'll call that even, and I'll look at the corresponding odd or even Hilbert transform. Okay, so the idea is that the theory for the maximum function traditionally has evolved at the same time as understanding this convolution operator. This helps you typically natural space to study this guy, which is a multiplier. You just have to bound in the oscillatory interval. Okay, and so there are nice results. Every time we get a result for the singular interval, we can try to prove the same result for the maximum function. So that's the basic theme. So you'll start to appreciate the singular intervals coming into it, and we'll I'll try to make it dimensions a little bit more. So here's some theorems. So let me get quickly, sorry. So these are a lot of theorems with a lot of names attached to it, so I hope I can get this right. Let's look at the even one. Okay, and you can characterize L2 boundness as just a multiplier, and what you get is this is equivalent to looking at the slope of the tangent line. And it requires that doubles, that there's a constant bigger than 1, such that if I look at the slope over a dyadic interval, so I go from t to lambda t, I require the slope has to at least double. So that's called gamma prime doubling. So that characterizes the L2 boundedness for the singular interval operator. Okay, and then you can ask if it's true whether you get LT boundedness for the maximum for L2 boundedness. In fact, if the other observations if gamma prime doubles in this way, then in fact that's a sufficient condition to guarantee that this is bounded on L2. And what's more, is you can even do better, just give the characterization for all LP. Okay, so this is actually the content, the LP result, in this paper of 8. But the L2 result actually came earlier for the Hilbert transform in a paper of Nagel, Vance, Nagel, Vance, Wanger, and Weinberg, okay, for the L2 result. So that's the generalization. That would, of course, generalizes this TT squared, where we had this polygonalized TT squared. Of course, we were doubling the slope each time we moved from one dyadic interval to the next. So that is assumed in this result here. Okay, so this is a sufficient condition that guarantees boundedness for the maximal function. Now I want to look at a picture. Okay, so now I want to move to the odd extension. So here at a point T, I look at this tangent line. So the slope of this tangent line, of course, is